Alright, so this is our AP Chemistry Chapter 19 lesson video. This is part 3, and I'm going to cover section 19.6 and 19.7. So let's go. Hopefully, if you watched the previous video, you were understanding the whole relationship between delta G, delta H, delta S, and temperature. If not, we're going to keep talking about that today. Alright, so we're going to talk about the effect of temperature on the spontaneity of reactions, or of course, determining whether or not they're thermodynamically favorable or unfavorable. Okay, so what happens is we can plug positives and negatives into this formula. Remember, our formula is delta G equals delta H minus T delta S. Alright, so if delta H is negative and delta S is positive, remember T always has to be positive. That means this minus T delta S, it's going to be negative. Because see, these are both positive, that's negative. A negative and a negative make delta G negative, and so that is spontaneous or thermodynamically favorable. However, if H is positive and S is negative, when you have a negative of a negative, that's a positive. So really we have a positive and a positive. In that case, delta G is positive, and so the reaction is non-spontaneous or thermodynamically unfavorable, but the reverse reaction would be spontaneous or thermodynamically favorable. So those are the easy ones. The tricky ones are these two, because then you have to base it on temperature. Okay, so let's look at these options real quick. All right, so remember, temperature has to be positive because it's Kelvin. So it says delta H is negative, but delta S is also negative. So what happens is that makes this positive. So as long as delta H is negative enough, when I add this to it, delta G will still remain negative. But if this factor gets too big and too positive, it will overcome delta H and delta G would be negative. Positive. So the thing is, we have to focus on temperature. Okay, so we want this number to be small. So that means we want low temperature. So if this number is small enough, if the temperature is low enough, delta G will still remain negative. Okay, so it's spontaneous or thermodynamically favorable, but only at low temperatures. On the other hand, let's say we have a positive delta H and we have a positive delta S. Well, in that case, it's a positive number minus a number. So if I can get this number big enough, it will make the delta G negative. Because remember, that's the whole thing. If we want something to be thermodynamically favorable, delta G needs to be negative. So we want this value to be large. So at high temperatures, we can get a negative delta G, and that would make a spontaneous or thermodynamically favorable reaction. So remember, for thermodynamically favorable, we want negative delta H if possible, positive delta S if possible, and negative delta G. That's what will make a spontaneous or thermodynamically favorable reaction. Once you start switching these signs around, then other factors come into play, like temperature. Alright, so the Haber process for the production of ammonia involves the equilibrium of this. Assume that delta H and delta S for this reaction do not change with temperature. Predict the direction in which delta G for this reaction changes with increasing temperature. Okay, so here we have our reaction. We know that delta G equals delta H minus T delta S. Alright, and so we're predicting the direction in which delta G for this reaction changes with increasing temperature. So we are increasing the temperature of this. So we're trying to increase this. Alright, so first I need to pay attention to, of course, that delta S. Alright, I can see that on this side I have 4 moles of gas. On this side, I only have 2 moles of gas. So what does that mean for my delta S? So we know temperature is always positive. That means my delta S is actually negative. Okay, so my delta S is going to be negative because we are becoming more orderly. We went from 4 moles of gas to 2 moles of gas. Alright, so in other words, that means this whole value is going to be positive. Remember, we want, in order for it to be spontaneous, we want delta G to be a negative number. So this is a positive value, so we want it to be as small as possible. So if we're increasing temperature, that's actually not favorable. Okay, so as temperature increases, then delta G becomes, and this is where it gets a little weird, the wording on the AP exam, they don't just want to say you to say delta G increases or decreases because of the fact that a lot of times it's negative. They want you to talk about, is it becoming more negative or less negative? So you would say then delta G becomes less negative, or you can put more positive. So I'm just going to put slash more positive. Okay? So hopefully that one was okay for you. Hopefully you remembered how to figure out delta S for this one. And so again, I can't give any more information here because we weren't given delta H. Like if I had delta H, I could maybe get a little bit, closer to an actual number or determine if it's actually going to be negative or positive. They didn't give us delta H though, so we have to use what we got. Alright, so delta G becomes less negative, or like I said, you could put more positive. Alright, so it says calculate the values of delta G for the reaction at 25 degrees Celsius and 500 degrees Celsius, and then it gave me the delta H and the delta S. Okay, so I'm calculating delta G for two different temperatures. Alright, so the first thing I would obviously need to do is make sure I have my temperatures in Kelvin. So this, of course, is going to be 298 Kelvin, because I'm just going to add 273, and this is going to be 773 Kelvin. Alright, so I know that delta G equals delta H minus T delta S. Alright, so you have two options. You can either change the joules to kilojoules or the kilojoules to joules. It didn't specify what unit it wanted for delta G, but you've got to have them the same. Okay, so I have my kilojoules for delta H, I've got joules for delta S. I chose to change to joules, which is odd because usually I change to kilojoules. I'm not really sure why I did that again this time. Alright, so I just plug in. So what I chose to do was change this to joules, so I changed it to negative 92380 joules. Okay, so I just took my decimal, moved it over 3 places, or of course multiply by 1,000. So I plug in my delta H, so negative 92380 joules. That really should have been per mole. I might have left that off. Minus my T is 298 for the first one, times my delta S, which is negative 198.3 joules per Kelvin. Okay, so my Kelvin cancels. Oh, you know what? We didn't need moles for this one. I was about to say I didn't have moles in my answer. Alright, so here, let's get rid of that. Sometimes though it'll have per mole and the delta S will have per mole also. So since delta S didn't have per mole, I didn't need per mole there either. Alright, it just depends on what they give you. Okay, so I multiplied these two. Notice I have a multiplication sign here. This isn't me subtracting. And then I subtracted from that. And so I got negative 33,286.6 joules. So that is my delta G at 25 degrees Celsius. But notice it wants me to do it for both. So then I just do delta G at 500 instead. So I keep the same delta H. This time I have 773 as my temperature times my same delta S. Okay, because remember it told me at the beginning of this question, assume these don't change with temperature. Now we know they do change with temperature, but we're assuming they don't. Alright, and so once I solved this one, I got 60,905.9 joules. So did our answer from part A make sense? We said that delta G becomes less negative or more positive, and in this case it sure did. It was negative 33,000, and now it's about positive 60,000. Okay, so hopefully that was good. Alright, so let's move on. Alright. Let's see. Oh, yeah, sorry. I'm struggling today, y'all. I'm sorry, I'm tired. Alright, so practice exercise. So y'all try this one. Okay, you are, let's see, calculating delta H and delta S. Oh, you can't try this one yet. Hang on, I gotta give you numbers for these. Okay. Actually, we're gonna do a bunch like these, so maybe just watch me do this one because we'll have some more in the sample and practice because this has a lot of work behind it. All right, so what I'm going to do is I'm going to do my delta H up here and my delta S down here. I didn't give myself a lot of room to write. Okay, so here I'll give you a little reminder. I'm doing delta H up here and delta S down here. So remember, the way we calculate delta H is products minus reactants, but I have to pull those numbers from that appendix C. Okay, so for this one, the number is negative 296.9 kilojoules per mole. But what do I have to do to it? I have to multiply it by 2. So you're going to see me use negative 593.8 kilojoules. All right, delta H for any element in its natural state is 0. And of course, when I multiply 0 by 1, I get 0. All right, SO3 is negative 395.2 kilojoules per mole. But I'm going to multiply that by 2. So you're going to see me use negative 790.4 kilojoules per mole. Whoops, wait, remember the moles cancel. Sorry, I put moles right there. All right, so we just do our products minus reactants. Ooh, I'm going to have to write small, y'all. So I have my products right here, negative 790.4 kilojoules, minus my reactants, which are negative 593.8 kilojoules, plus, of course, 0 kilojoules. And so once I solved that, I ended up getting negative 196.6 kilojoules. Okay, so that would be my delta H. Now, it also wanted me to calculate delta S, so I would have to use my appendix C to pull the S values for all of these, the entropy values. Okay, so again, I'll put those up for us. So SO2, it was 248.5 joules per mole Kelvin. But of course, I have to multiply that by 2, so you'll see me use 497 joules per Kelvin. All right, oxygen is, remember, delta S for an element in a standard state is not 0. It's 205 joules per mole Kelvin, but I multiply it by 1, which of course still gives me 205. And then for SO3, it's 256.2 joules per mole Kelvin. And then, of course, I multiply that by 2, so I get 512.4 joules per Kelvin. Okay, so y'all, it really might help if you have out your textbook and are looking and finding these numbers in Appendix C. That's the only place I'm pulling them from. Okay, so obviously on the AP exam, they will be given to you. So delta S is just like delta H. It's products minus reactants. Okay, so then I just plug in. So my products are 512.4 joules per Kelvin. My reactants are 497 joules per Kelvin plus 205 joules per Kelvin. So once I solved that, I ended up getting negative 189.6 joules per Kelvin. All right, so again, y'all, all I'm doing is pulling these numbers from Appendix C in the textbook. Then it says, using the values obtained in Part A, estimate delta G at 400 Kelvin. So this is where I can now use my delta G equals delta H minus T delta S. So the only problem is, though, of course, delta S is in joules per Kelvin and delta H is in kilojoules. So let's see what I changed this time. I changed kilojoules to joules. Okay, so I guess I'm just going to do that same thing again. So I changed this to negative 196,600 joules, and so that's what you'll see me plug in down here. Because remember, we need it to either both be joules or both be kilojoules. It doesn't matter which. I mean, unless it specifies that it wants kilojoules or it wants joules, and then you go to that one. So I have my negative 196,600 joules minus my T, which is 400 Kelvin, times my delta S, which is negative 189.6 joules per Kelvin. So my Kelvin cancels, and then I have joules minus joules, which is fine. And so what I ended up getting was, goodness, where's the answer after all that? There it is. Negative 120,760 joules. And so, of course, if this was on the AP exam, you'd probably want to put this in scientific notation. Like you could do 1.21 times 10 to the 1, 2, 3, 4, 5. So you would do negative 1.21 times 10 to the 5. That would be a better way to write an answer like this on the actual AP exam. Okay, so finding all those numbers, that's the longest part of these. So like I said, on the AP exam, then they would provide you with those numbers. But if you need to see the numbers while I'm doing this, I'm pulling them out of Appendix C in your textbook. All right, so about free energy, and we're now going to connect it to equilibrium. So I know y'all probably thought, oh my gosh, equilibrium's gone forever. It's going to poke its head in a little bit in this chapter, and then a little bit again in chapter 20, but you know, it's not going to overpower everything. All right, so there is a relationship between delta G and the reaction quotient. Remember, the reaction quotient is just Q. So that's when we use amounts, concentrations, or pressures that aren't at equilibrium. So delta G is your delta G in standard state plus R times T times ln(Q). And R is 8.31 joules per mole Kelvin. Now we've used this R value before when we used gas laws, but the units were slightly different. It was liters times kilopascals over moles times Kelvin. But don't worry, this is on your formula sheet, okay? So you'll have both sets of units at the end of it. All right, so as we saw in section 11.5, the normal, I love how they acted so we remember this, all the way back to 11.5. The normal boiling point is the temperature at which a pure liquid is in equilibrium with its vapor at a pressure of 1 atm. So it's telling me when it's at its boiling point, we know that liquid and gas are at equilibrium. Write the chemical equation that defines the normal boiling point of liquid carbon tetrachloride, CCl4 liquid. Okay, well y'all, it's boiling, so that means we're starting with CCl4 liquid, and it's in equilibrium, so I do my double-sided arrow, and then that's going to be CCl4 gas. Okay, boiling is not a chemical change, so you're not going to have anything different on your products and reactant side besides the state of matter. Okay, so hopefully that one wasn't too bad. That was pretty easy. All right, then part B says, what is the value of delta G standard state for the equilibrium in part A? Okay, so in this case, we know it has told me that it is at equilibrium. So if you remember from our previous lesson video at equilibrium, delta G equals 0. Okay, at equilibrium, delta G equals 0. All right, so hopefully you remembered that. Otherwise, that one will be kind of tricky. All right, then it says estimate the normal boiling point of CCl4. Okay, well, y'all, I know that delta G is delta H minus T delta S. Okay, I know that. I have already decided that delta G must be 0. All right, I'm trying to solve for temperature, so we'll talk about that in just a second. But what am I missing here? I'm missing my delta H and delta S. Okay, but I can calculate those using stuff I know from Appendix C. All right, so first of all, let me solve for T. That's what I need to solve for first. So I'm going to subtract delta H to the other side. So that's negative T delta S. Then I'm going to divide both sides by delta S. That'll be negative T. So then to get rid of that negative, I can just do positive for both sides. So temperature is delta H divided by delta S. All right, so remember our reaction was this right here. CCl4 liquid, CCl4 gas. All right, so I got to figure out my delta H and delta S. Okay, they give us lots of practice calculating these, unfortunately. So this video might be kind of long. I apologize in advance. Well, it's not really in advance. We're already in the thick of it. All right, so again, I'm just pulling these numbers from Appendix C. So the good news is they're both 1 mole, so I'm not going to sit there and write the numbers twice. I'm just going to go ahead and get rid of the moles. Okay, so for delta H, this liquid is negative 139.3 kilojoules. And the gas is negative 106.7 kilojoules. For S, the liquid is 214.4 joules per Kelvin, and the gas is 309.4 joules per Kelvin. Okay, so first let me do my delta H. So remember, it's products minus reactants. So it's negative 106.7 minus negative 139.3. And y'all make sure you realize it's minus and negative, so really you're adding it. All right, so for delta H, I ended up getting 32.6 kilojoules, but of course, what's the problem? I'm going to get kilojoules and joules, so I've got to convert one of them. I just chose to convert this one to joules. All right, And so then I do the same thing for my delta S. So delta S is also products minus reactants. So I do 309.4 joules per Kelvin minus 214.4 joules per Kelvin. All right, and so once I subtracted, I got 95 joules per Kelvin. Okay, so now I'm ready to plug in. So my delta H is 32,600 joules. My delta S is 95 joules per Kelvin. So if you look, my joules cancel. I'm left with Kelvin, but it's in the denominator of the denominator, which pops it up into the numerator. And so for this one, I got, whoops, where's my answer? Where is my answer? Oh, there it is. Okay, it's only boxed in, but I couldn't find it. So I ended up getting 343.16 Kelvin. Just like that. Okay, so like I said, sometimes they might provide you with delta H, delta S. Sometimes they'll provide you with the values. But either way, you can use this formula to solve for T. Okay, as long as you have the other information. But the important thing to remember is at equilibrium, delta G is 0. Alright, so y'all try the next one. You're going to need some numbers, so if you'll give me a second, I'll put them up. So don't pause it just yet. Okay, so it says estimate the normal boiling point in Kelvin for elemental bromine. Okay, so our reaction is Br2 liquid is in equilibrium with Br2 gas. So let me go ahead and give you those delta H and delta S values. Whoops, I'm going to put H on top. So these just come from Appendix C in your textbook. Alright, so our delta H, of course, element in its natural state, bromine is naturally a liquid, is 0 kilojoules. But once it's a gas, it's 30.71 kilojoules. And since they're both 1 to 1, I'm not going to write that I multiplied it by 1 mole. Alright, my delta S, on the other hand, is 152.3 joules per Kelvin. And for the gas, it's 245.3 joules per Kelvin. Okay, so y'all pause the video, try it. I'll assume you've done that. Let's look at it together. Alright, so my delta H is just products minus reactants, so it's 30.71 kilojoules minus 0 kilojoules, which of course is 30.71 kilojoules. My delta S, on the other hand, is 245.3 joules per Kelvin minus 152.3 joules per Kelvin. And so my delta S ends up being 93 joules per Kelvin. But of course this is joules, this is kilojoules, so I changed this one to joules also. Alright, so we know we're using this formula, delta G equals delta H minus T delta S. But remember, we are at the boiling point. At the boiling point, you're at equilibrium, so delta G equals 0. So I'm just going to show you how to rearrange the formula one more time. So I'm going to minus delta H from both sides. I'm going to divide both sides by delta S. And then both sides are negative, so I can just change them to positive. So T is delta, whoops, sorry, this should say delta H on top, is delta H divided by delta S. So then I just plug in. So my delta H is 30,710 joules. My delta S is 93 joules per Kelvin. Those joules cancel, I'm left with Kelvin, and I got about 330 Kelvin. Alright, so hopefully you got that one right. Obviously, if this was on the AP exam, they would have to give you this in parts or something like that on free response. Otherwise, they might give you the delta H and delta S, but they shouldn't have you calculate this much stuff on one part. That would just be much too time consuming, as you just saw. Alright, so now it says calculate the delta G at 298 Kelvin for a reaction mixture that consists of 1 atm nitrogen, 3 atm hydrogen, and 0.5 ppm ammonia. And then it gives me delta G is negative 33.3 kilojoules per mole. Alright, so I know that my reaction is this right here. They gave it to me earlier. So N2 plus 3H2 equals 2NH3. So what they're telling me is we have 1 atm of this, we have 3 atm of this, and we have 0.5 atm of this. Okay, now they did not tell me those are equilibrium values, so I need to be thinking of Q. Alright, so let's write our Q. Our Q is, of course, just like K, products over reactants. So my product is pressure of NH3, but but it has a coefficient, so I'm going to square it, divided by pressure of the nitrogen times pressure of the hydrogen. But I'm going to cube that, okay? After we're deep in equilibrium, y'all kind of start forgetting about the whole squaring and cubing because you're so used to just everything being 1 to 1. So don't forget that. All right, so now I can plug in. So I have 0.5 ATM squared over 1 ATM times 3 ATM squared. So all I did here was just plug these values in, okay? Because of course Q you can use any amount. So I have 9.26 times 10 to the negative 3. Okay, so y'all, they told me that delta G is negative 33.3. Oh, sorry, I should have had a little knot here. That's at standard state. So now I can use that formula I showed y'all at the beginning of the slide. So delta G is delta G naught. Naught is just the little degree sign. We call it that. That means at standard states, of course. Plus RT ln Q. Okay, so I just start plugging in. So one thing I do need to point out is your R value. If you remember all the way back, it's 8.31 and then it deals with joules. But what did they give me delta G in? Kilojoules. See how this is a common thing. Like, why can we not all get along? I don't know. Okay, so this is negative 33300 joules per mole instead. Okay, so 33,300. So I plug that in. Plus, my R value is 8.31 joules per mole Kelvin. My T is, what did they tell me? Oh, 298 Kelvin times natural log of my Q, which is 9.26 times 10 to the negative 3. Okay, so yeah, all we're doing is just plugging into a formula and solving. All right, so plugged all that in, and so if you look, my Kelvin's going to cancel, and I end up with joules per mole, which is fine. And so when I solved, I got that delta G is negative 44,894.54 joules per mole. Now, of course, you could have done this in kilojoules instead, and you would have ended up getting about negative 44.9 kilojoules per mole. Because, of course, remember, you really want to stick to about 3 significant figures if this was like a free response question on the test. All right, so hopefully that one wasn't too bad. It's just a lot of math today in these sections, which a lot of you are really good at the math ones, so we should all be glad. All right, so you can also relate it to K, of course. If you can relate it to Q, you can relate it to K, because Q and K are related. So another formula is delta G is negative RT ln K. Or if you need to rearrange to solve for K, you know how some of y'all have trouble doing the inverse of natural log. It's E raised to the negative delta G divided by RT. The more negative delta G is, the larger the value for K, which makes sense because K means we want a lot of products. So that means the reaction must be thermodynamically favorable, so delta G must be negative. Okay, so the more negative delta G is, the bigger K is, the more chance there is to make products. If delta G is positive, then K is less than 1, because that means it favors reactants. All right, so next sample exercise. Oh my goodness, so much math. That's okay, y'all. We just got this, and then we're done. Yep, just this one page. All right, we got this. All right, so use standard free energies of formation. So, of course, I'm going to pull those numbers from Appendix C to calculate the equilibrium constant K at 25 degrees Celsius for the reaction involved in the Haber process, which is, of course, nitrogen and hydrogen making ammonia. The standard free energy change for this reaction was calculated in sample exercise 19.9, and so your standard delta G is negative 33.3 kilojoules per mole. So thank goodness we at least don't need to waste time recalculating that. All right, so we're looking for K, so we're going to use the formula from the previous slide that was solving for K. So of course for that one, K equals E to the negative delta G divided by RT. Okay, so all of that is the power. Okay, it gave me my delta G right here, but of course the problem is that R value is 8.31 joules per mole Kelvin. So I'll go ahead and change this to joules again. Okay, and then of course my temperature, I just need to add 273. So that's 298 Kelvin. And so then y'all just plug in. So E raised to the negative. I'll put it in parentheses. Negative 33,300 joules per mole over the R, which is 8.31 joules per mole Kelvin, times the temperature, which is 298 Kelvin. Okay, now technically writing all these units makes no difference because does K have any units? No, it doesn't. But the important thing is also remember this is negative, but you still keep the negative in the front. Okay, don't try to be like, oh, okay, well I already have a negative. You need both negatives. All right, so once I solved for this, I ended up getting, like here, I'll just kind of clarify this a little bit. Like once you do all this up here and the negative of the negative, it ends up being e to the 13.4. And so once I plug that in, I ended up getting 660,003.2. And of course, there's no unit. And of course, K values, a lot of times we put in scientific notation. So you could do 6.60 times 10 to the 1, 2, 3, 4, 5. Just like that. So remember, no units for K. Okay, don't be trying to pull down joules per mole and all that kind of stuff. Okay, no units for K. Alright, so hopefully that one wasn't too bad. So y'all try the next one. Alright, and see here I just had 7. I rounded to one significant figure, but remember on the AP exam, normally go out 3, so that's why I did the 6.60. Alright, so y'all have a similar one, so you are calculating the delta G and the equilibrium constant for the following reaction. Okay, so let me give you some numbers real quick before you try this one. Okay, since yours didn't give you the delta G, I went ahead and used my appendix C for that. So these right here are actually the delta G numbers. Okay, like you can look up delta H, delta S, or delta G in your appendix C. So I went ahead and looked up delta G numbers. And so for hydrogen, it was 0 kilojoules per mole. For bromine liquid, it was 0 kilojoules per mole. And for HBr, it was negative 53.22 kilojoules per mole. But of course, I have to take into account my coefficients. So of course, this was just 0 kilojoules, 0 kilojoules, and this one became negative 106.44 kilojoules. Oh, sorry, I forgot to say pause it and try it on your own. Okay, forget that I just did all that part. Pause it and try it on your own. Okay, so you're going to solve for your delta G, and then you're going to solve for K. So I'll assume you've done that, and now we'll continue. Okay, so delta G, delta H, delta S, they're all just products minus reactants. Okay, so delta G, my product is negative 106.4 kilojoules, and then I'm just going to minus a 0 and a 0. So minus 0. So obviously it's just this right here. Alright, but we all know what's going to happen. I'm going to have to change this to joules anyway. So here is your delta G. That was one of the things it told me to calculate, but it also told me to calculate my K. Alright, so remember, K is just your E to the negative delta G over RT. So it's E to the negative. So I grab my delta G, negative 106.440 divided by R, which is 8.31 joules per mole Kelvin, times my temperature, which in this case they gave me Kelvin, 298 Kelvin. Alright, so once I solve for that, just to clean this up for you, when you put all this in, it ends up being E to the 42.98. And so once I did that, I ended up getting 4.6 times 10 to the 18. So this reaction definitely wants to go to completion. Because look how large this K value is. That means it highly favors the products. Which makes sense because we got a nice negative delta G. Alright, so hopefully you got that one right. Like I said, I just pulled those delta G numbers from Appendix C. Alright, so sample integrative exercise, and then we can move on from this chapter. So it says, consider the simple salts sodium chloride and silver 1 chloride. We will examine the equilibria in which these salts dissolve in water to form aqueous solutions of ions. So here's what happens. They just both break apart. Calculate the value of delta G at 298 Kelvin for each of the preceding reactions. Okay, so for this one, what I did was I just looked up those delta G values in Appendix C. Okay, since they're all 1 to 1, I'm just going to write what I got from Appendix C. Okay, so I just looked up delta G values for these. So for sodium chloride, I had negative 384.0 kilojoules. For the sodium ion, I had negative 261.9 kilojoules. And for the chloride ion, I had negative 131.2 kilojoules. So of course, to do delta G, it's just products minus reactants. So I did the negative 261.9 kilojoules minus the 131.2 kilojoules, and then minus the reactants, which is negative 384 kilojoules. And so for delta G, for the sodium chloride, I ended up getting negative 9.1 kilojoules per mole. Okay, so that's what I ended up getting for the sodium chloride. But then I got to do it for the silver chloride, okay, because it wants them for both. So I looked up the delta G values for this in Appendix C. So for this one, I got negative 109.70 kilojoules. For the silver ion, I got 77.11 kilojoules. And for the chloride ion, again, it's just still negative 131.2 kilojoules. So my delta G, again, is products minus reactants. So it's the 77.11 kilojoules, or technically minus 131.2 kilojoules, and then minus the reactants, which is negative 109.7 kilojoules. So y'all, what you have to be careful of is all these like negatives and double negatives and things like that. It's very easy for y'all to put these in the calculator wrong, even when you know what you're doing. So I got 55.61 kilojoules per mole. Okay, so in other words, what I can see is, since this is my delta G, sodium chloride dissolving in water is thermodynamically favorable, whereas silver chloride dissolving in water is not thermodynamically favorable because it has a positive delta G. So that means, just they didn't ask yet, but that means this would have a large K value, this would have a small K value. Okay, that might be where they're headed. We'll see you in a minute. All right. So it says the two values from part A are very different. Is this difference primarily due to the enthalpy or the entropy? Now, we didn't calculate delta S or delta H, and gosh knows we don't want to calculate that again. So let's just go back and look. Okay, the entropy should be pretty much the same. It's a solid breaking up into two aqueous ions. So see how it's a similar process? So your entropy term should be pretty similar. So that means the huge difference has to be due to enthalpy. Now, it'd be one thing if one of them was making a gas or something like that, then entropy might have been it. But it's definitely going to be your enthalpy. All right? So then it says, use the values of delta G to calculate the KSP values for the two salts at 298 Kelvin. See how all we're doing is taking the delta G values I just calculated in part A, so I'll put them back up, to calculate our Ks. All right, because we know how to do that. So here, I'm going to have to do one up here, though. All right, so K, and I'm just going to call it sub SP. It doesn't matter. Like, I'm just throwing that on there so you realize we're doing the same thing. Is E to the negative delta G over RT. Okay, so up here I'm going to do NaCl, and down here I will do HCl. So here, let me get rid of this so I have room to write. Okay, so remember, we're going to need to change those delta G's to joules. All right, so it's E to the negative. Now for sodium chloride, I ended up getting negative 9.1 kilojoules per mole. So what I was plugging is negative 9,100 joules per mole over my R value. Whoops, I didn't make my parentheses big enough. 8.31 joules per mole Kelvin times my temperature. It told me we are at 298 Kelvin. All right, and again, if you have trouble solving for these, I'll always clean this up. All right, and so don't forget that double negative here. Okay, so it ends up being E to the 3.67, and so I got 39.25 for my K value, which makes sense because we decided a lot of the salt will dissolve, so having a large K value makes sense. Now we decided not much of the silver chloride is going to dissolve because delta G was positive, so let's see if that happens. All right, so my delta G for the silver chloride was 55.61 kilojoules per mole. So that would be 55,610 joules per mole. Then I divide by my 8.31 joules per mole Kelvin and times my 298 Kelvin. Okay, so again, today's just a lot of math. A lot of math. So when you clean up this area, it ends up being e to the negative 22.5. And so that gives me 1.69 times 10 to the negative 10, which makes perfect sense. Delta G was positive for this one. That means it does not favor reactants. It does not, I'm pointing towards the products, but said reactants. It does not favor products, it favors reactants. So I have a very small K value. Okay, so that was part C. Oh, goodness. Almost done, y'all. Almost done. This video is kind of long. Uh-oh. Okay, there we go. Whew, thought my clicker was broken. All right, so part D, it says sodium chloride is considered a soluble salt, whereas silver chloride is considered insoluble. Are these descriptions consistent with your answers in part C? Well, yeah, if we look, we got a KSP of about 40 for NaCl, and we got 1.9 times 10 to the negative 10. So is that consistent with the fact that we say this is soluble and this is not? Yes, it is. All right. Then part E says, how will delta G for the solution process of these salts change with increasing temperature? What effect should this change have on the solubility of the salts? Okay, so here we have our delta G equals delta H minus T delta S. We know T is positive. Okay, we know entropy. Here, I'm going to click back real quick. We can see we have a solid splitting up, so we know our entropy is also going to be positive. Okay, so that means this value right here, this whole value is going to be negative, like we're subtracting from the delta H. Okay, so what that means is both of our delta S's are positive, so this whole thing is going to remain negative. So in other words, as temperature increases, because this number is just going to get bigger and bigger and more negative, that's going to cause delta G to get more negative. Then we can say delta G becomes more negative. Or you could say less positive. Either one. Okay, more negative or less positive. And then it says, what effect does that have on solubility? Well, the more negative delta G is, the more soluble. So solubility increases. Just like that. Okay, so y'all, you've got to understand that notice how many of these questions relate back to the delta G equals delta H minus T delta S. So just constantly have that in the back of your mind while you're doing these types of problems. All right, and we are done with chapter 19.